This problem and all other Calc 135 problems here at Rutgers can be found in Sarai Studies. Link is in the description box below. In this video, I'm going to be introducing to you the big idea of calculus, also showing you the difference between average velocity and instantaneous velocity. So the first point is that velocity really just means slope. So essentially, anytime they ask you find velocity, all they're really asking you is find the slope. And so per that definition, then we know that the formula for velocity is really just the same formula as slope, which we know is y2 minus y1 over x2 minus x1, right? The change in y over the change in x. But of course, with velocity, we use different variables, but this is the essence of it. And finally, the third point is that average velocity and instantaneous velocity are the exact same thing. It's the same formula. The only difference is that for average velocity, they're always going to give you 2 points, and you can simply just plug that into the slope formula. For instantaneous velocity, they only ever give you 1 point, and that should make sense because you're trying to find the velocity at an instant in time, at 1 point in time. So your job, because you know that you need 2 points in order to use the slope formula, is to find a second point, and that second point just has to be very, very close to the given point. In this video, I'm going to be proving to you why these points are true. There's also a fourth point that I wanted to mention. I will include it in the end of the video, but there's average velocity, there's instantaneous velocity, and there's also exact velocity. And all exact velocity is just instantaneous velocity as h, which I will explain when we get there, gets really, really small, basically 0. And this really is the essence of calculus. So let's start with what you know. In high school, if there's one thing you learned is how to find the slope of a line. Well, how do we do that? Well, to find slope, we need a line, and we need 2 points on that line, because we could just take 2 points, and this could be, let's say, x1, y1, and this could be x2, y2, and then slope would be just the difference between the y's and the difference between the x's. So y2 minus y1 over x2 minus x1, and that's your slope. But what if I change the x-axis to represent time instead? So now we have t for time, and the y is just going to represent the position at every point in time. So x is position. You can think of x marks the spot, so x marks the position at every point in time. And now the points just change up their variables. So instead of x, it's just t, so time 1 and time 2. And instead of y, well, y really just represents the position at that time. And so now those are our coordinates. And now we could just revise the slope formula to match the variables, but it's the same idea. You have x and y, 1, 1, and you have x2, y2. So same thing. What's your y2? It's the position at time 2. What's your y1? The position at time 1. All over the difference between x2 and x1. So that's time 2 and time 1. So this is our revised slope formula. It's the same thing. The only difference now is that instead of x, we have time, and instead of y, we have position. So this is the slope formula, but guess what it also is? This is your average velocity formula. So this proves point number 1, that anytime you hear velocity, they're just asking you for slope, because that is what it is. It's slope. It's just the difference between the position over the difference between time. So we already proved point number 1 and essentially point number 2. But let's go ahead and prove point number 3. So let's say that this is the graph of the curve, and I ask you to find the slope at a specific point in time, at t1. And so the point would be t1, comma, whatever the position is at t1. So again, I'm asking you to find the slope at a particular instant in time, or at a particular point in time. But you have to think, how can I do that? If in order to find slope, I need a line, number 1, and this is most definitely not a line, it's a curve. And number 2, I need 2 points. And I most definitely do not have 2 points, I just have 1. So the question is, how can we find the slope given 1 point? And the answer is we can't. It's impossible, because in order to find slope, you need 2 points, essentially meaning you need a line, because at least 2 points make up a line. So if we know that in order to find slope, we need a line, and notice how this is a curve, then I'm going to show you something really cool. So this is the same curve on Desmos. And let's say I'm trying to find the slope at a particular instant in time, and let's say that time is 2 seconds. So right about here. So we're looking at this from the perspective that t1 is 2, and we're trying to find the slope at this particular instant in time. So notice how it's a curve, right? If I go ahead and zoom in on 2, notice what the graph becomes. What does it look like now? A line. And so the idea is that if we zoom in on a curve at a particular point, let's say 2, we're always going to see a line. So I'm going to go ahead and move it over here. If I take a screenshot, at 2 is over here. At 2, what do we have? We have a line. And so because we're trying to find the slope at this particular point in time, right, at t is equal to 2, because we have a line, we can just pick any point on this line and find the slope using those 2 points. And so if this point over here is 2, we get 2 from down here, and then what is it? It's 64. And then the second point is just a point that's really, really, really close to this point. It's just a little bit more farther away. So it would be, I don't know what it would be, but we would probably say maybe 2.01. Maybe we're going to call that 2.01 over here. And then the y value would be whatever y value is over here. I already know what it is. It's 64.6416. It doesn't fit in there, so let me rewrite it. And so now we have our 2 points, and we can plug it into the slope formula and get the instantaneous slope. Because the idea is that this change in time is so small that there's practically no difference between these 2 points. And so when you're finding the slope, number one, you're satisfying the fact that you need 2 points in order to find the slope. But number two, because these 2 points are so close together, the change in time is so small, there's practically no difference between the points. And so you're essentially just finding the slope of this point at this exact point in time at t is equal to 2. And so the main idea is that the smaller the change in time is, the better approximation of slope you're going to get. And so what does that look like over here? Well, again, we have our tangent line, which is just the line that briefly touches the instant in time we're trying to find the slope at, or the point we're trying to find the slope at. And because we have a line now, we can pick 2 points on that line. And so clearly we already have 1 point that's always going to be given to us. But then the second point we need to pick, and it needs to be on that line. And so that second point is just going to be really, really, really close to the point we're trying to find the slope at. And so essentially all that means is that we're taking time and we're just adding a little bit more, just a little bit more. So we're adding h. H just stands for a little bit more. And so now the new x value is really just the time we're trying to find the slope at plus a little bit more, essentially just becoming time 2, t2. And so the coordinate for this is still t2, comma, the position of t2, just x, y, same thing, y'all. But we're just being more specific, and we're saying that t2 really is just t1, right, the time we're actually trying to find the slope at, plus a little bit more, and then the position at that new time, which is just the original time plus a little bit more. And so the idea, again, is that this length over here, this is the same thing as h, so we're just adding a little bit more to this time. You can think of it, the change in time. You want the difference between the times to be so small that basically they're on the same line. That's the idea, because we need a line, and we need 2 points on that line to find the slope. And the only way to get those 2 points on the same line is if the distance between those 2 points is really, really small, that they're very close together. And so we can come up with 2 formulas. And so just like we did over here, we can come up with a slope formula. In this case, this is my x1, y1. Here, this is my x2, y2. We're just going to use these coordinates first. So my y2 is this, my y1 is this, my x2 is this, and my x1 is this. And so notice, this is average velocity. This is instantaneous velocity, and like I said, they have the same formula. But again, the only difference between both of these is that for this one, we're only actually given 1 point. We have to find the other point, and the other point is really just this point plus a little bit more. And so the way we can represent that to be more specific is using these coordinates here. So forget about this one. This is really x2, y2. So y2 is this. It's the position at t plus a little bit more minus the original position. And then t2 is the time plus a little bit more. That's time 2. Minus t1, which is just time. And this is also instantaneous velocity. Now here's the 4th point that I may add. We have something called exact velocity. And exact velocity is just the instantaneous velocity as h gets really, really, really small. So remember, h is your a little bit more. It's the little distance between these 2 points. H is also your change in time. Because look at what happens when I take this second point and h gets really, really smaller. Because remember, h is just the distance between the 2 points. So as h gets really, really, really small, so small, it gets to 0. Basically, there's no difference between the 2 points. Green doesn't exist anymore. The h doesn't exist anymore. What happens? It's the exact same point. So technically, when the difference between the 2 points is so small that there's practically no difference, we are literally finding the slope at this particular instant in time, at this specific point in time. And meanwhile, we're satisfying the fact that we're still using 2 points on a line. And so there's something really interesting when h gets limited to being 0. So it gets so small, that is equal to the exact velocity. And that is literally calculus. This is also known as the difference quotient. And look at what happens. These t's, they cancel out. You're just left with h, and that is your difference quotient. Instantaneous velocity is not the exact velocity because technically there is still some green, there is still some difference between the points. But when you take instantaneous velocity and you limit the difference to be 0, to basically not exist, you get the exact velocity. Because what you're doing is you're taking the difference between the 2 points, limiting it to be 0, so it's basically they're the same point, and so you're going to get the exact velocity, the exact slope at that specific point in time, and that's what you call the exact velocity. velocity. And so this is really the concept of calculus, the fact that you can limit the difference between 2 points to be 0, then you can get the exact velocity at a particular point. And so the question from earlier was, how can you find slope given only 1 point? This is how. Technically, you still need 2 points, but the difference between those 2 points is going to be so small. It's going to be basically the same point because the difference is literally going to be limited to 0. And therefore, on a technicality, it is still 1 point. So there is a technical answer to that question, and that is this. You will get the exact slope, the exact velocity of 1 point in time when you use this formula here, which you will learn how to use in the next video.